Look at this glow. It shouldn't exist. According to every textbook you've ever read, what you're seeing right now is a physical impossibility. Einstein told us that light is the speed limit of the universe. 300,000 kilometers per second, an unbreakable cosmic wall. But inside this pool of water, particles are doing something they aren't allowed to do. They are outrunning the photons. They are winning. This is a sonic boom of light, a visual scream from the subatomic world, and it might be the most dangerous thing you'll ever see. Is the speed of light a lie? No. But the way we've been taught to think about it is dangerously incomplete. To understand this, we have to travel back to 1934, to a laboratory in the Soviet Union that found the first crack in reality. A young physicist named Pavel Cherenkov noticed a faint blue light in a bottle of water. No one believed him at first. His colleagues thought it was just fluorescence. Common. Boring. They told him to go home and stop chasing ghosts. But Cherenkov was stubborn. He realized this light didn't care about the rules of chemistry. It was answering to a higher power, physics. He was seeing something that Einstein's relativity said was impossible. A particle moving through matter faster than the local speed of light. This discovery would lead to a Nobel Prize. It would track the birth of stars. And it would save lives in ways we never imagined. But what the government didn't tell you was where that light actually comes from and why it's appearing inside your own eyes. Let's start with the basics. You know that light is fast. In a vacuum, it is the undisputed champion of the universe. It travels at c. At this speed, time stops. Mass becomes infinite. Nothing with a heartbeat can ever reach this velocity. This is the iron curtain of physics. To break it, you would need more energy than exists in the entire universe. But here is the trick. Light doesn't always travel at c. In fact, it's quite the lazy traveler when things get crowded. When light enters water, or glass, or your own body, it slows down. It gets bogged down by the atoms in its path. In water, light loses about 25% of its speed. It becomes a sitting duck. And that is where the anomaly begins. Imagine a subatomic particle, like an electron, shot out of a nuclear reaction like a bullet from a high-powered rifle. This particle is moving at 99% of c. In a vacuum, light would still beat it. But in water, the particle wins. It is now traveling faster than the local speed of light. It has broken a fundamental barrier. And reality reacts violently. Just as an aircraft creates a sonic boom when it exceeds the speed of sound, this particle creates a luminal boom. The atoms in the water become polarized. They get excited by the particle's passage. They want to get rid of that extra energy. They release that energy as a flash of electromagnetic radiation. And because of the math of the universe, that flash is always blue. Wait, why blue? Why not red or green? Because higher frequencies contain more energy, and this is a high-energy event. But here is the problem. If you see this blue light outside of a controlled lab, you are effectively standing in a death zone. The glow is a signature of high-level ionizing radiation. It is the visual ghost of a dying atom. For decades, we thought we understood it. A simple optical effect. A quirk of the refractive index. But we were wrong. The mystery deepened when we started sending humans into space, away from the protection of Earth's atmosphere. In the 1960s, during the Apollo missions, astronauts began reporting something impossible. Something that shouldn't be happening inside a dark capsule. Even with their eyes closed, they saw it. Flashes of blue light, streaks of white, right inside their own skulls. Was it space madness, or were their eyes becoming biological detectors for the most dangerous particles in the cosmos? NASA panicked. If the astronauts were seeing radiation, it meant their brains were being pelted by cosmic rays. They needed an answer. They turned to the work of a man who had been dead for years, Pavel Cherenkov. The theory was simple. The liquid inside the human eye, the vitreous humor, was acting just like the water in a reactor. Cosmic rays were traveling through the astronauts' heads faster than light travels through eye fluid. A biological Cherenkov boom. Problem solved, right? Wrong. Because as the experiments continued, the flashes didn't match the math. Some flashes were happening at energy levels too low to create Cherenkov radiation. There was another player in the dark. This forced us to look deeper into the heart of the anomaly. To a place where the rules of light are even weirder. We discovered that the blue glow wasn't just a byproduct of speed. It was a bridge between the quantum world and ours. Think of it this way. The particle is a rock thrown into a perfectly still pond of electromagnetic fields. The ripples are the light. But what if the pond is already moving? What if the vacuum of space isn't empty? This led to the anomaly within the anomaly. Something called anomalous Doppler effects. Usually, when something moves toward you, the light shifts blue. Away it shifts red. We've known this for a century. But inside a Cherenkov-capable medium, the Doppler effect can reverse. The light shifts the wrong way. Time seems to run backward. The math gets rewired. The laws of causality start to bend. And suddenly we weren't just looking at a blue glow. We were looking at a way to see the invisible structure of reality itself. A cosmic cheat code. But every cheat code has a cost. And the cost of breaking the light barrier was about to be paid in blood. Leningrad, 1986. A reactor core is exposed. The air itself begins to glow with that beautiful, deadly blue. The workers knew what it meant. They called it the blue flash. It was the last thing many of them would ever see. The air was ionized. The Cherenkov effect was happening in the atmosphere itself. A subatomic fire that couldn't be extinguished. Firefighters rushed toward the glow. They didn't have Geiger counters. They used the blue light as their only guide to the heart of the disaster. But the blue light wasn't just a signal. It was a weapon. Every photon was a bullet, carrying the signature of a core in meltdown. Within hours, the Cherenkov tan appeared on their skin. A deep, metallic burn caused by the sheer intensity of the luminal boom. All was lost. The scientists realized they weren't just observing a phenomenon anymore. They were being consumed by it. Why couldn't they stop it? Because the Cherenkov effect is a runaway train. Once those particles are loose, they outrun everything, including our ability to react. In the chaos, a terrifying question emerged. If light can be outrun in water, can it be outrun in the vacuum of space? Einstein said no. But Einstein didn't account for the quantum vacuum, a sea of virtual particles that might act just like water. If space itself has a refractive index, then light is never truly at its maximum speed. There is always a loophole. We tried to build shields. We tried to contain the boom. But the blue light kept leaking through. It was a ghost in the machine. The anomaly was telling us that our maps of the subatomic world were wrong. We were looking at the effect, but missing the cause. We needed a new way to see. Not with our eyes, but with the very anomaly that was killing us. What if the blue glow wasn't a warning? What if it was a lens? A way to track the untrackable? The solution came from an unlikely place, the bottom of the world. Under 2 kilometers of solid, prehistoric ice. Here, scientists turned the entire planet into a Cherenkov detector, using the ice itself as the medium for the luminal boom. To understand how this works, we need to look at a speed boat. When a boat moves faster than the waves it creates, the waves pile up. They form a single, powerful shock wave. This is exactly what a particle does to light. By measuring the angle of that blue cone, we can calculate the exact speed of the particle, its energy, its origin. It's a subatomic GPS, and it's the only way we can find the ghost particle of the universe, the neutrino. Neutrinos are trillions of times smaller than an atom. They pass through you, the Earth, and the Sun like they don't exist. But once in a billion times, a neutrino hits an atom in the ice. It creates a secondary particle, a muon. That muon is traveling faster than light in ice. It triggers the blue glow. The silent alarm goes off. By seeing the Cherenkov light, we are effectively watching the shadows of the most mysterious objects in the cosmos. We are using a physics anomaly to build a telescope that doesn't use mirrors. It uses reality itself. But the story doesn't end in the ice. Because some scientists believe we can use this glow to break the ultimate barrier. If we can manipulate the Cherenkov effect, we might be able to create a negative refractive index to make light move backward. This isn't science fiction. These are metamaterials. cloaking devices, lenses that can see things smaller than a single photon. We are learning to tune the vacuum, to turn the universe into a medium where light is our servant, not our master. But wait, if we can make light slow down, can we make the vacuum thinner? Can we raise the speed limit of c itself? Some theoretical papers suggest that in certain extreme environments, like the event horizon of a black hole, light is already being outrun. They call it superluminal travel, a realm where the Cherenkov effect is the only thing that proves we are moving at all. But to go there, we have to face the causality problem, the monster that Einstein warned us about. If you travel faster than light, you arrive before you leave. You break the relationship between cause and effect. The blue glow is the universe's way of screaming that time is being shredded. It is a cosmic error message. Is it possible that the Cherenkov effect is actually preventing us from traveling through time? To find out, we have to look at the most controversial particles ever theorized: tachyons. Tachyons are hypothetical particles that always move faster than light. They never slow down to see. It's impossible for them. If they exist, they would be constantly emitting Cherenkov radiation, even in the vacuum of space. The universe would be bleeding blue light from every corner. And guess what? We've detected it. Scientists call it the cosmic optical background. A glow that shouldn't be there. A glow that matches the Cherenkov signature. Are we looking at the exhaust of FTL particles from the beginning of time? Or is something even stranger happening? Connecting the dots reveals a staggering possibility. The speed of light isn't just a limit, it's a temperature. Just as water turns to ice when it gets cold, space, time might have frozen light into a specific speed during the birth of the universe. And the Cherenkov effect is a melted spot. A tiny pocket where the old rules, the faster rules, still apply. It's a remnant of a more powerful universe. A universe without speed limits. This is the major revelation. The blue glow isn't a byproduct. It is the original state of the universe. Everything we see, the stars, the planets, our own bodies, are just the slow leftovers of a faster reality. We are living in the wake of a cosmic boom that happened 14 billion years ago. We are the Cherenkov light. If this is true, then FTL travel isn't about moving faster. It's about remembering how to move normally. But to reclaim that power, we must first master the shadow that the blue light casts. The danger we ignored, but there is a reason we fear the blue. In the history of nuclear science, the blue flash is the silent herald of the Reaper. 1946. Los Alamos, a scientist's screwdriver slips. For a fraction of a second, the room is bathed in an ethereal blue light. Louis Slotin knew exactly what that light meant. It was the Cherenkov effect happening inside the very air he was breathing. The radiation was so intense it outran the light in his eyes. He didn't just see the flash, he felt it in his DNA. He was a dead man walking. The blue light had rewired his biology. This is the dark turn, the anomaly as a weapon. We realize that the Cherenkov effect is the ultimate snitch. It reveals when we've pushed nature too far. It is the universe's alarm. In the 1980s, medical machines like the Therac 25 glitched. They delivered massive doses to patients who reported seeing a blue sparks. They weren't being treated. They were being bombarded. The anomaly was the only witness to a software error that killed. This forced a global reckoning. We had to build safeguards. We had to learn to respect the light we couldn't outrun. But how do you protect against something that moves faster than your own nervous system can process? The answer was to stop looking at the light as an enemy and start using it as a surgical tool. Today, we use Cherenkov detectors to ensure nuclear waste isn't stolen. It's the unforgeable fingerprint of plutonium. If the glow is there, the material is active. You can't hide it. You can't mask it. The physics won't let you. We've turned the blue ghost into a cosmic policeman, a guardian of the very power that once threatened to consume us. But the most beautiful transformation of this anomaly isn't in a reactor. It's inside a human being. Meet Sarah, a cancer survivor. Her life was saved by the very light that once signaled a meltdown. Doctors used Cherenkov imaging to see exactly where the radiation was hitting her tumor, in real time. Before this, they were shooting in the dark. Now, the body's own luminal boom acts as a spotlight. For the first time, we could watch the FTL particles doing their work, turning a physics error into a biological miracle. Sarah saw the flash, but she didn't feel fear. She felt the future. This is the mirror moment. When we look into the blue, we aren't just seeing a speed limit being broken. We are seeing our own ingenuity staring back. We took a cosmic no and turned it into a medical eyes. We mastered the boom. But what happens when we take this light back to where it came from? Back to the stars. In 10 years, Cherenkov detectors won't just be in the ice of Antarctica. They will be in orbit. We will use them to map the dark universe, to find the matter that light itself refuses to touch. If a distant civilization is using FTL travel, they are leaving a trail of blue breadcrumbs across the galaxy. We are building the lighthouses that will finally let us see the cosmic traffic of the neighbors we've never met. But the ultimate goal is more personal. It's about the engine, the Cherenkov drive. If we can generate these particles at will, we can push our ships through the vacuum like they are moving through a sea of energy. We won't just be traveling to the stars. We will be traveling on the wake of our own discovery. The speed of light was once a wall. Cherenkov showed us it was just a doorway. We just had to learn how to knock. Our ancestors feared the dark. We feared the blue. Our children will call it home. But as we move faster and faster, we must ask, are we escaping the laws of physics, or are we finally fulfilling them? What if the universe wants to be outrun? What if Fido is just the starting line of a much larger race? Perhaps the blue glow isn't an anomaly at all. Perhaps it is the only thing that is actually normal in a world of slow light. We spent centuries trying to reach the speed of light, only to realize that the most important things in the universe are already past it. Information, entanglement, gravity. They all seem to know where to go before the light arrives to tell them. Einstein's speed limit holds true for the vacuum, but the Cherenkov anomaly proves that light is not an absolute, it is a variable. If the vacuum itself has a hidden structure, a quantum foam, then we haven't actually seen the universe's true top speed yet. We are like deep sea fish, thinking the speed of sound in water is the fastest thing possible, unaware of the atmosphere above. One day, we may find a way to thin the vacuum, to move between the particles of space-time itself. That is the dream of FTL. Until then, the blue glow remains our only reminder that the impossible happens every day inside our reactors and our eyes. It is the sound of a barrier breaking, a luminal boom that tells us the universe is far more flexible than we imagine. We aren't just observers of the light. We are the explorers who learned how to outrun it, and we're just getting started. The Cherenkov effect is just the beginning. In our next video, we investigate why some physicists think the universe is a hologram. If you enjoy videos that go deeper than headlines and actually explain how the world works, you're in the right place. Subscribe to the channel so you don't miss the next breakdown. Hit like if this video helped you see something differently. And if you have a question or a topic you want explored next, drop it in the comments. Your curiosity drives this channel.